For the lesson on polygons, we have the following learning competencies. The learner first illustrates polygons, its convexity, angles, and sides, derives inductively the relationship of exterior and interior angles of a convex polygon, and lastly, solves problems involving sides and angles of polygons. Plane figures are made up of points that are all in the same plane. They lie on a flat surface. A plane figure is either an open or a closed figure. Some plane figures are called polygons. A polygon is a closed figure which is the union of segments called sides such that these segments called their sides are non-collinear, and non-collinear segments look like this and not this. Second, each segment or side intersects two other sides only at their endpoints called their vertices. Let's have this example. So looking at these two sides AB and CB, they intersect at point B. These sides AC and BC intersect at point C. Okay? And sides AC and AB intersect at vertex B. Okay? And points A, B, C are what we call the vertices. Let's have some examples and non-examples of polygons. These two figures are not polygons simply because they are not closed figures. Then how about this figure? This figure is not a polygon, though it is closed, since we have here two collinear segments. And at the same time, in this point, we have four sides or segments intersecting at this point. Okay? And lastly, this figure is not considered to be a polygon since not all parts are made up of segments. These are curved figures. The next one is, of course, examples of polygons. These are all closed figures in which every two segments or sides intersect at one point. Okay? Then how do we name a polygon? We name a polygon according to its number of sides. Okay? So we can easily remember them by looking at the prefix. Tri for triangle, quadrilateral for four-sided polygons, pentagon, penta for pentagon, we have hexagon, heptagon, seven-sided polygon, octagon, eight-sided polygon, nonagon, nine-sided polygon, decagon, 10-sided polygon, dodecagon, 12-sided polygon, and of course n-gon. Okay, we're just making use of n for those n-gon for those polygons in which the number of sides is more than 12. Now these polygons can either be convex and concave. Okay, so what are convex and concave polygons? Okay, so we have convex and concave polygons can be used also to identify whether a polygon is regular or irregular. A figure is convex if every line segment drawn between any 2 points inside the figure lies entirely inside the figure. For example, we have here these two figures. Notice that if you're going to connect any 2 points, the segment is contained in the interior of the polygon. Even if you're going to add more points, then connect any 2 points, okay, still all parts of the segment are seen in the interior of the polygon. Same is true here. Okay, so all parts of the segments, whenever we connect every 2 points here, are all found in the interior of the polygon. Next, how about concave? A concave polygon is, of course, the opposite of convex polygon. Okay, looking at these two figures here, okay, notice that if you're going to connect these 2 points here, some parts of the segment is not found in the interior. Okay, though some segments are contained in the interior, but not all can be contained. Okay, so looking at this, most parts of the segment are found in the exterior of the polygon. Same is true here. So whenever there is one segment whose some parts of it are not found in the interior, automatically the polygon is considered to be concave. So going back to our previous examples, okay, so we have here a triangle this is convex. Okay, this trapezoid is convex. Why? If you're going to connect any 2 points here, they are all contained in the interior. Okay. How about this pentagon? Okay. Okay. This is still convex. How about this hexagon? This hexagon, of course, convex. And this heptagon. If we're going to connect these 2 points here, okay, a part of this segment is not found in the interior, so this is concave. How about this? This is convex. And obviously, this one is concave because if you're going to connect these 2 points here, okay, some parts of the segment are not found in the interior of the polygon. So this is concave. This one also is convex. And this one is obviously concave. Okay? So not all segments are found in the interior of the polygon. So this is concave. Okay. Let's continue. Now, let us now define regular polygons. So when can we say that a polygon is regular? Regular polygons are polygons which satisfy the following properties. Okay, all of these properties must be satisfied. If one of these properties is not satisfied, then a polygon is not regular. So these are the properties. It must be convex. It must be equilateral, mean to say all sides have equal length. Then it must be equiangular, mean to say all angles have equal measure. Then, the equal number of tick marks shown in the sides or angles of polygons show equivalence on the said parts. Okay. Now, looking at this example, we have a square, okay, and this regular hexagon. And looking at the tick marks also, we can say that, okay, the square is convex. Same is true with the regular hexagon. Are all of the sides equal? With the number of marks shown in the sides of the polygons, they are all equal, mean to say equilateral. The two polygons are both equilateral. Then looking at the angles here are all 90. The angles here are all the same because of the equal number of marks. So therefore, these two polygons here are regular polygons. Okay, let me correct some parts of this. Let me add one more mark here. Okay. So why is it that these two polygons are not considered to be regular? Looking at the first property, okay, it must be convex. Yes, a rhombus is convex. It must be equilateral. Now, looking at the opening or the measure of each angle, this angle is obtuse, whereas this one is acute. Obtuse, acute. So not all of the angles are congruent, mean to say this is not equiangular. Okay. But of course, these sides are equal, so this is equilateral but not equiangular. That's why this polygon is not considered to be a regular polygon because one of the properties is not satisfied. How about a rectangle? A rectangle is convex. It is convex. It must be equilateral, okay? Are all of the sides equilateral or the same? No. Not all of the sides are equal. So, the second property is not satisfied. Therefore, a rectangle is not a regular polygon. We are already done with the first learning competency. Let's move on now to the second and third ones. We have derive inductively the relationship of exterior and interior angles of a convex polygon and solve problems involving sides and angles of a polygon. So from the activity, we can now derive the triangle angle sum theorem, which states that the sum of the interior angles of a triangle is 180. Say for this triangle ABC, okay, the sum of its interior angles is simply by adding the measure of angle A plus the measure of angle B plus the measure of angle C, which is equal to 180 degrees. Now we are going to make use of this triangle angle sum theorem to determine the sum of the interior angles of convex polygons. Let's have this investigation activity. So, what we are going to do is, we are going to determine the number of triangles contained in the polygon by drawing the number of diagonals from one vertex only. Then after that, we are going to complete this table. Okay, so the first two rows are already completed. Say for a triangle, it has number of sides. The number of triangle is of course 1 here. The sum of the interior angles is 180. Then for the quadrilateral, okay, it has 4 sides. The number of triangles is only 2. So mean to say 180 plus 180 is equal to 360. For a pentagon, from this vertex, okay, let's determine the number of diagonals that can be drawn. We have 1, 2 diagonals are drawn. Then we have how many triangles here? We have 3 triangles drawn. So mean to say we have 3 180s. A pentagon has 5 sides. Number of triangles formed 3. Then we have here 3 times 180 is equal to 540. How about this hexagon? A hexagon has 6 sides. Let us now determine the number of triangles that can be drawn or contained inside the hexagon through the diagonals. We have this diagonal, second, and the third. So we have how many triangles drawn? We have 1, 2, 3, 4. So we have 4 triangles, mean to say we have 4 180. We have 4 times 180, and that is equal to 720. I think this is now enough for us to determine the pattern, okay, and find out the formula in determining the sum of the interior angles of convex polygons. So with this, okay, let us relate it from the number of triangles and the number of sides. Of course, this is the number of triangles, okay? We're going to relate it to the number of sides. Now, what must be subtracted to 3, 4, 5, 6 in order to get the number of triangles 1, 2, 3, and 4? So looking at this, in order to get 1, we have to subtract 3 by 2. Then, to get 2, subtract 4 with 2. Same is true with 5 and 6. We're going to subtract each with 2 or by 2. Okay. So, notice that this is held constant, minus 2. And then what is changing is the number of sides. Say the number of sides is n. So, this is the number of sides. Mean to say, the sum is equal to the number of triangles times 180. The number of triangles can be determined by subtracting 2 from the number of sides, and that is n minus 2 times 180. So we have now the theorem, the sum of the interior angles theorem. If a convex polygon has n sides and S is the sum of the interior angles, then S sub n is equal to n minus 2 times 180. So if you happen to forget this formula, always go back to this investigation activities. So from this theorem, we have corollaries. The first corollary is the number of sides of convex polygon is n is equal to S sub n over 180 plus 2. Now, how is this derived? We have derived this one from this equation. Say n is unknown. Okay, so we have S sub n. Okay, we're going to apply the distributive property of multiplication. So we have S sub n is equal to 180n. Negative 2 times 180 is negative 360. Apply the addition property of equality. So we have S sub n plus 360, which is equal to 180n. Then divide all terms by 180 so that n will be determined. So we have now n is equal to, of course, this cannot be simplified anymore, S sub n over 180. 360 divided by 180 is equal to 2. Okay. So that's it. Then we have another corollary. The measure of each interior angle of a regular polygon with n sides is equal to the sum, which is n minus 2 times 180 over the number of sides. It is actually the sum, the S sub n over the number of sides, in which S sub n is equal to n minus 2 times 180. Okay, that's it. Let's have some examples. Find the sum of the interior angles of a decagon. A decagon is a polygon with 10 sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Then you are asked of the sum of the interior angles. So we simply make use of the formula S sub n is equal to n minus 2 times 180. So we have now S sub 10 is equal to 10 minus 2 times 180. And that is 10 minus 2 is equal to 8 times 180. And that results to 1,440. So the sum of the interior angles of a decagon is 1,440 degrees. Next is, how many sides does a convex polygon have if the measure of its interior angles is 2,340? Okay, so given here is the sum, okay, 2,340, and you're asked to determine the number of sides. So we can make use of the corollary. N is equal to S sub n over 180 plus 2. So we have the sum is 2,340 over 180 plus 2. 2,340 over 180 is equal to 13 plus 2, and that is 15. Thus, the polygon has 15 sides. Okay? So we have here a 15-sided polygon. Okay? Okay, let's have another example. Find the measure of each interior angle of a regular nonagon. Okay, a nonagon is a polygon with 9 sides. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we're looking for the measure of each interior angle, and then of course to determine the measure of each interior angle, we have to know the sum of the interior angles, and we can make use also we can make use of the corollary. The interior angle of a regular polygon can be determined by the sum over n, and that is n minus 2 times 180 divided by n. So we have n is 9 minus 2 times 180 over 9. So we have 9 minus 2 is 7 times 180 divided by 9. So we have 7 times 180 is equal to 1,260, and divide it by 9. So we have here 1,260 divided by 9 is equal to 140. Thus, the measure of each interior angle of a regular nonagon is 140 degrees. Let's have another example. Find the number of sides of a regular polygon if each of its angles has a measure of 120 degrees. So the given here is the interior angle, okay, which is 120, and the number of sides is unknown. So here we can make use of the corollary. Interior angle is equal to n minus 2 times 180 over n. Okay? So let us now substitute. The interior angle is 120 equals n minus 2 times 180 over n. We get the cross products now. It is understood to be 1. 120 times n is 120n. Then we apply the distributive property here. N times 180 is 180n. Then negative 2 times 180 is negative 360. And then we're going to apply here the subtraction property of equality. So we have 120. Okay. We have minus 180n is equal to negative 360. 120n minus 180n is equal to negative 60n equals negative 360. So dividing both sides by negative 60. So the regular polygon has 6 sides. Let us now investigate the sum of the exterior angles of polygons by determining first the measure of each exterior angle of the polygon shown and then add them together. Okay, let's start with the triangle. Now, looking at the two angles here, the interior at exterior angle, we can see that the two angles are supplementary or a linear pair of angles. So what we are going to do here now is simply get the supplement of the interior angle. And that will be done also to the rest of the interior and exterior angles of the polygons shown here. So the supplement of 45 is 135. The supplement of 105 is 75. And the supplement of 30 is 150 degrees. So adding all the angles, we have 135 plus 75 plus 150. That sums up to 360. Okay. Let's move on to the quadrilateral. Okay. The measure of each interior angle is 90 and the supplement of 90 is also 90. So all of the exterior angles here measures 90. So mean to say we have 90 times 4 is equal to 360 also. How about this hexagon? We can see that we have here a regular hexagon in which the measure of each interior angle is 120. So meaning to say the measure of each exterior angle here is 60, 60, 60, 60, 60, 60. We have 6 60s here. Adding them all together, we have a sum of 360 degrees. This only shows that regardless of the number of sides of a convex polygon, okay, the sum is always 360 degrees. Thus, we have this polygon exterior angle sum theorem, which states that the sum of the measures of the exterior angles of a polygon is 360. And we have here a corollary. The measure of each exterior angle of a regular polygon with n sides is simply dividing 360 by the number of sides. Now, from this equation, we can also determine the number of sides by, of course, let's derive it. Okay, we have now EA, exterior angle, times n is equal to 360. So we need the number of sides. So divide both sides by the exterior angle, the measure of each exterior angle. Then the number of sides can be determined by simply dividing 360 by the measure of each exterior angle. So let's have some examples for this. Example number 1. How many degrees are there in each exterior angle of a regular pentagon? So n here is equal to 5. Okay. Then you're asked of the exterior angle. So the exterior angle can be determined by 360 divided by n. 360 divided by n by 5. Okay. So 360 divided by 5 is equal to 72. Okay. So the measure of each exterior angle of a regular pentagon is 72 degrees. Next, if each exterior angle of a polygon is 45 degrees, how many sides does a polygon have? So, we simply make use of the formula. N is equal to 360 over the measure of each exterior angle. So we have 360 over 45, and that is equal to, N is equal to 8. So the polygon has 8 sides. Next, if each interior angle of a polygon measures 140 degrees, how many sides does a polygon have? Okay, let's visualize it. Okay, we all know that the interior angle of a polygon and the exterior angle of a polygon are supplementary. Okay. It's quite easy to determine the number of sides if we make use of the exterior angle of the sum of the exterior angles of polygons. So the interior angle here is 140 degrees. So the supplement of 140 degrees is 40. Okay. So we can make use of n is equal to 360 over the measure of each exterior angle to determine the number of sides. So we have now 360 divided by 40 is equal to 9. Thus, the polygon has 9 sides. The last one, okay, find the measure of each interior angle of a regular polygon with 10 sides. Okay, so again, we go back here in the relationship between the interior and the exterior angles of polygon. Find the measure of each interior angle that is unknown with a polygon with 10 sides. 10. So first is we are going to determine the measure of the exterior angle by dividing 360 by 10, and that is 36. Okay. Now, the exterior angle is 36 degrees. Then we are going to look for the measure of the interior angle, which is the supplement of the exterior angle. So we have here the interior angle plus exterior angle is equal to 180. So we have the interior angle is equal to 180 minus the exterior angle. So the interior angle is 180 minus 36, and that is equal to 144.